Hello, everyone. Sir Isaac Newton was once quoted as saying, "If I have seen further, perhaps it is because I have stood on the shoulders of giants." It's generally understood that one of those giants that he was talking about was a man known as the wandering mathematician, Johannes Kepler. And after watching the movie, you got to see some interesting pieces of the life of Johannes Kepler, and the man whose data he stole, Tycho Brahe, of the gold nose, and the Danish nobility and the greatest naked eye data ever assembled. And Johannes Kepler took that data, did hundreds of pages of calculations, and came up with what are known as Kepler's three laws of planetary motion that you saw in the Mechanical Universe video. So I just kind of want to summarize what they are for you here. Kepler's first law, sometimes known as the law of orbits or the law of ellipses. Kind of depends. There's kind of different names depending on who you read. But basically, the first law says that all planets move in elliptical orbits with the sun at one focus. Right? This is a violation of the Aristotelian viewpoint of perfect circles. Right? That everything had to be moving in perfect circles. Right? And so Kepler said, no, actually it was ellipses. So let's talk a little bit about ellipses, right? So if this is a very eccentric ellipse, way more elliptical than any of the planets in our solar system, right? Here's the sun at one focus. If we put a coordinate system in the middle here, right, there would be a point in space, there's nothing physically here, which would be the other focus. Together, they are called foci, to do the Latin, right? So the sun is at one focus, and the other one is here. Now, by the way, the word focus, as I thought it was an interesting thing they talked about in the movie, is Latin for fireplace, right? And Kepler was the first one to call it a focus, right? Because it's the sun at one focus. Now, this distance from the center to the far edge is called the semi-major axis. Okay, from the center to the far edge. On the other hand, this other one is called the semi-minor axis, right? The 2 points, the closest and the farthest from the sun, are very interesting points that we often look at. The closest point is called perihelion. The furthest point from the sun is called aphelion. If you're confusing which one is which, when I took an astronomy class in college, the professor told us how to remember this, and I still remember it to this day. He said, when you are close to the sun, you are in peril. Hence, you are at perihelion. I don't know, it worked for me, right? So I remember which is which. Perihelion and aphelion. Some interesting things go on at those points, and we will look at those in various points in this unit. Now, the distance from the center to either focus is a distance we call E times A, right? It's some fraction of the semi-major axis. That fraction, E, is what's known as the eccentricity of an ellipse, right? It's basically how far off from a circle it is. Technically, it's the ratio of the distance from the center to either focus and the semi-major axis. So if you take this distance, right, and divide it by the semi-major axis, you will get the eccentricity of the orbit. The more eccentric it is, the more elliptical it is. I measured this eccentricity. It is about 0.648. We're going to see some examples here in a moment of different planets, but that is way more eccentric than any of the planets in our solar system. For example, the eccentricity of Earth is a paltry 0.0167. In fact, it's so close to a circle that Kepler thought it was a circular orbit around the sun. He just thought the center of the orbit was a little bit off the sun, right? But his data, even Tycho's best ever naked eye data, was not good enough for Kepler to figure out that the orbit of the Earth around the sun was actually an ellipse. But thankfully, he attacked Mars, and that gave him some different answers. So we're going to take a look at a simulator here just briefly. It's kind of cool. It's from the University of Nebraska. Let's see here. Go here. Here it is. Okay? And this is going to allow us to kind of look a bit at Kepler's first and eventually his second laws. Okay? So I'm going to take the eccentricity here and turn it up a bit. I'm going to put it to look like, oops, let's make it 0.648. So it looks like my diagram, right? See how that pretty much looks as eccentric as the one that I drew? So there's the sun at one focus. I can show you the empty focus. There it is over there, right? I can show you the semi-major axis. Here's the center, right? Semi-major axis from the center to perihelion. The semi-minor axis, by the way, is this other axis. It doesn't really come into play in our physics, but it is, the smaller of the two. And then I can, let me turn off a couple of these things here. I can put this into motion. Now you'll notice here the animation rate is in years per second. So this is 0.2 years is going by every second. You'll notice some interesting things about the motion of that planet, right, when you're dealing with things. Now, let's jump to what Kepler did. Right? Kepler studied Mars. Well, actually, before we go to Mars, let's go to Earth. Here is Earth's orbit. Now, you notice the other focus, you can't really see it. It's inside the sun. Right? And the center, of course, is way inside the sun. You can't see that at all. Right? In fact, the eccentricity here, 0.0167 or 0.017 to 2 sig figs, is so circular that Kepler couldn't tell it wasn't a circle. He just thought it was off center a little bit. But we go to Mars with an eccentricity of 0.09, 0.093. It was just eccentric enough, here's the center, right? Just eccentric enough that with Tycho's best ever naked eye data, Kepler could figure out it was actually an ellipse. Some other cool things we can do in here. Watch this. So if I put the radial lines in, one of the things I liked about how they started out the movie was showing you how to draw an ellipse. If you take a string, right, and you put the string around two pegs at either focus, right, the distance from one focus to the circle, to the planet, to the other focus, and back again is a constant. So you put a loop of string around it, and you can draw out the ellipse. This is actually showing you that the calculations work out this way. Don't worry so much about the units. You can see them change slightly, but notice the total's always the same down here. Let me turn those off for you. One of the other cool things, we can put in other solar system orbits. So here's the planets that are inside of Mars, right? My very educated mother. So that's Mercury, Venus, Earth, and Mars. We can even we can label them. Kind of fun. And we can put the solar system planets in there. Don't ask me why it puts another one on Mars, right? This is the one we're looking at, but you can see all the other ones. You can get an idea of the period of all of them. Do you see how Mercury goes around fastest, and then Venus, and then Earth, and then Mars? That's indicative of one of Kepler's laws, which we'll get to. If we go out to the visible planets with the naked eye, that's all the way out to Saturn, right? You can see here that the inner planets are kind of close into the sun compared to the radius of Saturn's orbit. If we go out even further, this one includes Pluto as a planet, because that's when it was made. So if we go all the way out to Pluto, watch what happens. Now you can see Pluto is a quite eccentric orbit, still nowhere near the one I had in my PowerPoint, but still a little more eccentric. But if you notice, when I first did this and played with this, I went, wait a minute, why did the planet stop moving? Why did Pluto stop moving? Then I realized if you watch really carefully, it is moving, but really, really slowly. Pluto has a very long period. It takes a very long time to go around once. If we turn up the animation rate, now every second that goes by is 2 Earth years. These are Earth years. You can see Pluto start to move. Right? The other little interesting thing to see out here is Neptune. Notice that there's a short period of time when Neptune is actually further away from the sun than Pluto is. Now, sometimes students will ask, well, will they ever hit? No, because this is a two-dimensional representation of three-dimensional solar system. So the orbits of Neptune and Pluto never actually intersect. They're at different angles, right? So they don't actually touch. But in terms of flattening it out in 2 dimensions, right, Neptune is sometimes slightly further away than Pluto is. Watch what happens if I zoom back in. Let's go back to Saturn. Look at those planets in there, right? If they're moving 2 Earth years every second, Earth's going around twice every second, right? And Mercury is just flying. So if I take this back down again so we can see it, right? And so we get the idea here that Mars was just eccentric enough for Kepler to be able to see that it was actually an ellipse, right? That the data fit an ellipse more than anything else. So this is Kepler's first law. We'll come back to this simulator when we get to the next one, the second law. So let's go back. Here we go. So Kepler's second law is a weird one. It's called the law of equal areas. It says that a line connecting the planet to the sun sweeps out equal areas in equal times. Okay, now you'll notice here that all 3 of Kepler's laws are observational things. They don't give any reasons for this. And Kepler did not have Newton. Kepler is pre-Newton, right? So he didn't have anything that Newton knew to be able to explain these things. He sometimes had some vague ideas about why the planets orbited the sun. He was firmly Copernican, right? And, was a little bit scared of that because, remember, Galileo got imprisoned or put under house arrest for the last 8 years of his life for believing and explaining how the planets could move around the sun. But Kepler was firmly Copernican. But, he came up with these observations. And they showed you a bit in the movie how he did this. And it took pages and pages and pages and pages of calculations to deal with the decades of nightly data that he stole from Tycho Brahe. Okay. So let's go back to the orbital simulator again. And I'll show you what I mean by sweeping out equal areas in equal times. So let's go to Kepler's second law. I'm going to come back in here. I'm going to reset this thing. I'm going to put in an eccentricity to look like our original one. It's just a little bit easier to see what's going on, right, if you have a nice eccentric orbit. And then, so I'm going to start the animation. And then what I'm going to do is, so what this law says, okay, is if we take a certain amount of time there and a certain amount of time there, same amount of time, right, it's saying that these areas are the same. And in fact, they are. They are, if you actually measure them, they are exactly the same amount of area. Kind of interesting, right? Let me show you what this kind of cool thing here. Watch this. Ready? Those are all equal amounts of time, right? So those are all equal areas. Right? So an equal amount of times, a line from the sun to the planet sweeps out equal areas in equal time, right, as we follow it along. Interesting, right? Okay, so that's what the second law says. Now, there is a consequence to the second law, a corollary, if you will, that you can clearly see with this eccentric of an orbit. What can you see about the speed of the planet? Right? Obviously, it's not constant. It's not moving in a circle, right? Where is it faster? Right about there, right? When it gets closer to the planet. So the closer a planet is to the sun, the faster it moved. And Kepler was able to tease that out, right? And he thought it was kind of interesting, and maybe that had some deeper implications. But again, he didn't have F equals ma and all the kinds of things that we have because of Newton, right? But he thought that it was very interesting that planets move faster the closer they are to the sun. Okay, so that's a little corollary that's important. Now, we will eventually talk about why that is from the physics that we know, but let's leave it for now. Okay. Kepler's third law, sometimes known as the law of harmony, or I've heard it called the law of harmonies. Okay. This is the weird one and very mathematical. After doing lots of calculations, he found that the square of the period of a planet, right, around the sun, planet's orbit around the sun, is proportional to the cube of its semi-major axis. In symbols, the period squared is proportional to the semi-major axis cubed. Right? This is for any planet that is orbiting the sun. Okay? If you take the period and you compare it to the semi-major axis, right, this is the relationship. Now imagine the calculations that went into something like this, considering that he didn't have a Cartesian coordinate system and graphing and graphical analysis and things like that. Because I'm going to show you this. Okay? Here I made some graphs with graphical analysis. The top one is period versus semi-major axis. And this is for all 8 of our planets and Pluto. I threw Pluto in anyway. Right? You'll notice here that when I put the planets in, here's the Earth, right? Third rock from the sun, so these go in order, that you get a little bit of a curve right here on a period versus semi-major axis. By the way, this is period in seconds and semi-major axis in meters. If you go on the web, you'll see this done with lots of different units. You sometimes find the period in days, Earth days. Right? And the semi-major axis could be in something called astronomical units, AUs, which is the distance from the mean distance from the sun to the Earth, the radius of the Earth's orbit, is 1 AU. So they kind of relate everything to the Earth, right? Earth days and Earth radii, really. Radii of the Earth's orbit. Sometimes they'll do this in Earth years. Right? So there's different ones, but however units you use, you still get this kind of top opening parabolish kind of graph. But if you square this, square the semi-major axis, right, it doesn't quite work. So to linearize it, look what I had to graph. Period squared, so second squared, versus semi-major axis cubed. Oops, come back here, you. Go away, you. Period squared versus semi-major axis cubed in meters cubed. And look, that gave us a linear graph. And the numbers I used for period and semi-major axis are probably more, well, I know they're more precise than those Kepler would have had, because these are data I got off the internet based on, satellite measurements, not naked eye measurements, right? So this is really precise stuff. You'll notice here that the slope of this linearized graph is roughly 3 times 10 to the negative 19th seconds squared per meter cubed, right? And that's the ratio, that's the constant of proportionality, the slope of this graph. That's also the ratio of any planet's period squared versus its semi-major axis cubed, right? If you put this in a ratio, they all get the same constant of proportionality because the slope is constant, because it's a linear graph. This number works out to be some interesting numbers depending on the units. If you use period in, I believe, Earth years, and the semi-major axis in astronomical units, this works out to be 1, which is kind of interesting, right? But this is the one in base units. You also see what looks like a really big y-intercept, but it's actually really tiny if you compare it to 5% of this huge number up here, right? And notice the correlation is a 1. So this is showing us that, in fact, Kepler was right? But using modern techniques to linearize as opposed to pages and pages and pages and pages and pages of geometry and years of calculations, right, that he did to prove this. Kepler thought this was like a really deep idea. He thought he had understood the mysteries of the universe, right, with these kinds of 3 ideas. In fact, one of the interesting things that they showed in the movie, that little, what looked like a toy he was dealing with all those like shapes nested inside of shapes, right? That was a thing where Kepler was using the Platonic solids, which are objects that have plane faces that are all the same size. The one you're probably most familiar with is the cube, right? In a cube, all of the plane faces are the same size. There's a tetrahedron, which looks like a, what does it look like? Looks like a pyramid, right? You got the cube, you've got the dodecahedron, the icosahedron, and the tetrahedron, right? Different numbers of sides, okay? There's only 5 of them. Only 5 of those exist. Well, this is what he did, okay? He took a sphere. Inside of the sphere, he fit a cube. Inside of that cube, he fit a sphere that touched the inside edges of the cube, right? Inside of that, he put another one of the Platonic solids. Inside of that, he put a sphere. And he kind of built this little model. You see what I'm saying? Putting different Platonic solids and the spheres inside of them. And he found this weird relationship. He found that the ratio of the radii of those spheres was exactly equal, or pretty darn close to being equal, to the ratio of the radii of the orbits of the planets. Right? So this little device he was struggling to build with these Platonic solids embedded inside spheres and spheres embedded inside the Platonic solids seemed to explain to him how you could view the universe. Now, we know the universe is not a bunch of Platonic solids inside of spheres, right? But it gave Kepler a way of visualizing and conceptualizing the universe, right? And it was different than the Aristotelian viewpoint of these crystal spheres rotating around, right, with planets and stars embedded in them. So it was a different kind of viewpoint. They've actually got no relation to one another whatsoever. It's just this complete fluke of geometry that the ratios of the radii work out to be the same as the ratio of the radii of the planets. But it's just this cool thing. And he thought that that was like, the music of the spheres, the music of the universe. And he was, finding the way of writing it, really, which is why this one's called the Law of Harmony. Kepler was an interesting dude, as they talked about in the movie, right? I mean, his mother was tried for witchcraft. He had a bunch of kids, but he didn't see them much. When he found the time, he would wander around and help different people solve mathematical problems, hence his name, the Wandering Mathematician, right? But this is the third of Kepler's laws. Now, one interesting thing that you can do with Kepler's third law is you can compare two things that are orbiting the same planet, right? Like, if you compare two planets that are orbiting the sun, the ratio of their period squared to their semi-major axis cubed, right? The ratios are equal. Like I showed you here, for the planets orbiting around, right? Each ratio is roughly 3 times 10 to the negative 19th seconds squared per meter cubed. So this allows us to compare this ratio for one object to another. For example, we could take two planets that are orbiting the sun and compare them. We could take a satellite that's orbiting the Earth and compare it to this ratio of something that we know about and know a lot about since antiquity that is also orbiting the Earth, namely the moon. So if we take the period of the moon squared to its semi-major axis cubed, we could relate that to a satellite. Want a certain period for your satellite, right? What semi-major axis do you need? You could use this equation to relate the two. And this is some things that you're going to be doing in the next Google quiz, concept builders, and worksheets here as we go. So Kepler's 3 laws of planetary motion. The law of ellipses. The planets move in elliptical orbits with the sun at one focus. The law of equal areas in equal time. A line from the sun to a planet sweeps out equal areas in equal times. The only way that can work is if the planet moves faster, the closer it gets to the sun. And the law of harmony, the square of the period is proportional to the planet's semi-major axis cubed. Right? This ratio is true of all the planets that orbit the sun. And, like I said, it works for any objects orbiting some mass. Take, for example, the Galilean satellites, which are the moons that orbit Jupiter. Right? If you take any one of those, they have a ratio which is the same as all of the other moons' ratio. Now, it's not the same as the planets orbiting the Earth, right? But it's still the same ratio. Now, you do have to be careful of one thing. They've got to be orbiting a mass, not a point in space, right? So it's got to be two things that are orbiting the same mass, because the mass of the thing that's being orbited will play into this when we build to Galileo and then through to Newton.